Here we go again with another problem from, this time, 9E, assignment 9E. In this problem, this is a free response from AP, Physics C, 1976 M3 is the problem, and we're going to solve it. For the first part, we want to determine the final speed of block M. Block M is sitting at rest initially, a bullet with mass M and velocity v0. Is going to hit block M, go through it, and actually the bullet is not going to embed itself. It's going to go through and out the other side. We want to find the speed of block M afterwards, after the bullet makes its way through. This is a conservation of momentum problem. Momentum total equals momentum total after. So the momentum total originally is the momentum of the bullet, which is just mv0. That equals the momentum after, and after this collision, we're going to have the bullet leaving with speed mv over 3, which is given. And we need to solve for the velocity of block M. So that's going to have mass m times v prime. We need to solve for v prime. We have 2/3 mv0 equals mv prime, and therefore v prime equals 2mv0 over 3m. So a fairly straightforward application of conservation of momentum. In part B, we're going to say the block is fixed now, so it does not move, and the bullet comes out the other side with 1/2 the velocity original that it had in the beginning, so it's going to lose some of its speed. Block's going to stay put. We want to determine the loss of kinetic energy of the bullet. That would be kinetic energy initial minus kinetic energy final. It's not the other way around. Kinetic energy initial is 1/2 mv0 squared minus kinetic energy final is 1/2 m 1/2 v0 squared. So the loss in kinetic energy, the reason the initial is first here is because we're calculating loss. We're not calculating change in. If we were calculating change in, it would be the other way around. Over on this side, we have 1/8 mv0 squared. Over here, we have 4/8 mv0 squared. So our loss of kinetic energy is 3/8 mv0 squared. That's how much kinetic energy the bullet loses. Part C is kind of a different problem than we're used to seeing. In this problem, we want to calculate the minimum thickness L that a fixed block would have in order to stop a bullet. So here I have a diagram showing a bullet entering the block. It's going to go a distance L before it comes to a stop. The whole block is motionless, so the bullet's coming in and slowing down. And we're given that the force is constant, and we can use information from the prior problem. We are given force and distance, and we have kinetic energy. All these things should make you think of the work energy theorem, and that is work, which is also equal to FD cosine phi. Now we can use this equation. Why? Because force is constant in this problem. We have to use an integral of force with respect to displacement if we don't have a constant force. So we take the easy way this time, constant force, and phi, the angle between the force and displacement. The bullet's going to move this way while the force is an opposing force. So we're going to have 180 degrees here for the angle phi between displacement and stopping force. All of this is going to equal the change in kinetic energy, which is kinetic energy final minus kinetic energy initial. The displacement is going to be the block's length. Force, all we know is it's F, and this is times -1. this is going to equal kinetic energy final, which is 0, minus kinetic energy initial, which, if you remember, was 1/2 mv naught squared. So for the situation of the fixed block, we're going to have FL equals 1/2 mv naught squared. All right, now we need to take a look at, that's the case of the stationary block. Now we need to go back to part A with the sliding block and apply this exact same scenario. So we're going to have the same force, because it's similar materials, times not L, but L naught in the first case. And this is also going to be multiplied by -1, as this is a retarding force where the force is this way while the displacement is this way. So we have a phi angle of 180 degrees. This will equal change in kinetic energy, which for that bullet, kinetic final minus kinetic initial. Kinetic final in that case was given, well, the velocity after, I don't think we calculated it yet, 1/2 times m times 1/3 v naught squared. 1/3 v naught was the exit speed out of the wood, and the initial speed was still 1/2 m v naught squared, or the initial kinetic energy. This here is going to be 1/18 m v naught squared minus 1/2, which is 9/18 m v naught squared. The negatives are going to cancel. We have F L naught equals, it's going to be -8/18, which is going to be 4, well, the negative goes away, 4/9 m v naught squared. Now, we want to solve for L in terms of L naught. So we have L equals m v naught squared over 2f. Let's do a substitution here, and what would make sense is to get rid of f, as that's not one of the allowed variables. And let's solve this for f, and we'll plug that in here. So we have f equals 4m v naught squared over 9l naught. This we're going to stuff into here. So if my algebra is capable, I have m v naught squared all over 2 times this. 4m v naught squared over 9l naught. This mv naught squared is going to cancel. So I have L equals 1 over 8/9, 8 over 9L naught. Using the reciprocal, 9/8 L naught is equal to L. So L equals 9/8 L naught, and I think that's it. We have done it. The MVs disappeared. Okay, in part D, we're asked to compare the speeds, or come up with an explanation as to why there is a greater speed with the block that is held fixed versus the block that's free to move. A couple different ways to answer this. One is to look at the amount of time, the amount of distance the force would act. If we start with the case where the block is held fixed, cannot move, that means the bullet is going to travel a distance the width of the block. It's going to go through here, it's going to come out the other side. So the force is going to act from here to here. Now if that block is allowed to move, it's going to start out, the bullet's going to come in and start out hitting it, but because the block is in motion, the bullet will not come out until, for example, here, when the block is moved. So in this case, the bullet is actually moved a larger distance. It's moved whatever the width of the block is, plus however much that block slid. The distance for the sliding block is greater than the distance for the fixed block. Given more distance, more time for the force to act, it's going to decelerate the bullet more. So we expect it to exit with less velocity, less speed in the case of the sliding block. So another way to look at this is work. Work equals change in kinetic energy, and which one is going to do more work and change the kinetic energy the most, slow it down the most? The one with the greater distance. As the distance is greater in the sliding case, more work is going to be done on that bullet, which is going to decrease its kinetic energy the most. So using either Newton's laws or the work kinetic energy theorem, they both work. This is the end of 1976 M3.